we can move to the next speaker, Vladimir Gligorov from CNRS in Paris, who will update us on CODEXb detector.
Yeah, no. So thank you very much for the invitation to present what's going on with CODEXb here. And okay, you know, we've just discussed, so I don't think I need to motivate very much why we're interested in long-lived particles here. So let me just go directly to slide 3 and try a little bit to explain the point of why we propose to do this thing. So if you look here, you have the diagram essentially of the LHCb experimental cavern. LHCb is on the right. And then on the left, you have the old Delphi cavern with Delphi as a museum exhibit now. And the point of this area is that for LHCb upgrade 2, the aim is now to collect 300 inverse femtobarns at this interaction point. So contrary to today, this is not really a low luminosity interaction point anymore. Of course, it doesn't have the same luminosity as Atlas and CMS will, but it's not, it's quite substantial. And you get actually quite a lot of shielding for free from various things. So basically, if you put a detector of some kind in the area of this pink box, and you put some kind of lead veto, lead shield, which you see here on the this rhomboid here, you can get a zero background environment with a reasonable acceptance and a reasonable reach. And because LHCb is essentially a triggerless experiment from next year onwards, you can just go directly into the readout with it. And in case you see anything, you can actually look at what LHCb saw in the same event sort of for free. So this is quite nice without any real need for triggering or anything like that. And this is kind of our one slide summary of the complementarity of CODEXb with other things that are being proposed. And really the point is that CODEXb is sort of in trying to cover the same kind of space as Methuselah and Alex and so on, which is sort of transverse, and trading some reach compared to the others for we think significantly smaller costs and complexity. So this is sort of a little bit the timeline at the moment. And our idea is basically to operate a demonstrator during run 3, really validate the backgrounds, use this to fully optimize and minimize really the needed lead shielding, and then scale up during LS3 and LS4. Okay. So here are some, you know, obligatory reach plots. One for the B2SX models, where you have on the left and the right, depending on what you assume is the off-shell Higgs contribution. And this is kind of pretty representative. What you see, if you look at the green, which is like the LHCb region, you see at CODEXb basically quite neatly fills in at 300 inverse femtobarns, quite neatly fills in a large part of the acceptance. It's quite complementary to LHCb in this sense. And it doesn't have the same reach, of course, as Methuselah. But as I say, it's also a far smaller thing. And then yeah, you can put the reach anywhere between these two plots depending on what you believe about the off-shell Higgs contribution. This is another way to look at the complementarity with LHCb in terms of the branching ratio versus C-tau space, where you see the LHCb reach in sort of green and dashed blue, and you see the depending on the mass of this particle, the CODEXb, the estimated CODEXb reach in these solid lines. And then you can look at Higgs decays directly. So again, this is one of the areas where having something transverse, whether it's CODEXb or Methuselah or something else, is really complementary to ship and phasor, etc. And you see here the comparison with depending on the mass of this this A prime. And again, you don't do as well as Methuselah, but you complement Atlas quite nicely, especially at low masses. And then we can look at ALPS. I mean, all these plots are. I realized at some point I should have added a reference to the slides, but all these plots are from our EOI. So you can look again here with universal fermion couplings, and you see CODEXb in blue, and again you see that it's very complementary to LHCb, and in these models does quite well compared to phasor. Again, obviously not as well as Methuselah. And you can also look at heavy neutral leptons. So for the tau, for the tau channels, and you see again here that that has some reach beyond what the B factories and A62 would do. That's quite comparable to phasor 2. Okay. So let's talk a bit. So I hope that first part has sort of motivated a little bit why we think that this is a kind of nice thing to pursue. I also, because if we're hoping to actually discover something and not just exclude things, then having multiple experiments that have a chance to see the same thing is obviously by construction very important in this area. So if we look at the backgrounds, so what's been done is we simulated having this lead shield, and the idea is to have an active veto in the shield to reject secondaries produced in the shield, and having and then we simulated how much would actually get through and decay inside the detector volume. The bottom line is really on the far right of this slide, which is that essentially what you worry about is residual neutron on air and some very small amount of K longs that might get through. But most of the backgrounds can be perfectly well. Almost all the backgrounds can be perfectly well vetoed, and these expected yields are with the full, with the full 300 femtobarn data set. So then to validate this, we went ahead and did a measurement campaign in 2018. We just took 2 scintillators and basically put them in various areas in this, because this pink area here is currently a barrack where LHCb's trigger used to live. The trigger is now going upstairs, and so we put them in various areas there and measured the backgrounds, and you see sort of we took measurements obviously with the beam off and the beam on, and actually we get very significantly lower fluxes compared to what simulation would have told us to expect. And we attribute this basically to having additional shielding here. I don't know if you can see my mouse pointer, what I'm circling around, but additional shielding in this area around the vertex detector, which wasn't included in the simulation. But okay, this is a setup with 2 scintillators. Okay, so we want to validate this a bit more carefully because you don't want to be too optimistic. So now we're building a 2-meter cubed prototype with RPCs that were designed for the Atlas upgrade for the new small wheel. So there's 14 triplets in total. And this is meant to go in where the trigger server room used to be. So the space has been cleared out and so on of the racks. So it's quite convenient for a demonstrator because you get all the power supplies and facilities and so on for free, essentially. And you see you have a cube, and then inside the cube there's just one layer here as well, which then allows that we observe things that decay inside. They leave a few hits then. So this is going to be integrated. This demonstrator should also validate the readout. So this part, since LHCb is triggerless, and since the RPCs for the Atlas upgrade essentially end up using the more or less the same protocol that LHCb is going to use for its upgrade for the readout, we can send the data to the same backend readout boards that we're using for the rest of the LHCb detector. In fact, one for the demonstrator, one backend FPGA card is enough to read out and maybe even reconstruct. This is under investigation. And so this is what we expect as backgrounds of demonstrator. So the demonstrator doesn't have any LED shield, okay? So, but this is good because it means we get more backgrounds and we can measure them and compare them to simulation. And the point of this table is if you look at Codex beta, which is the middle column, then the K-long contribution, which is the right-hand column. I mean, you see that you will get many multi-track K-long decays, or you expect many multi-track K-long decays. And this is very nice because we can hopefully also then use this to study how well we can geometrically discriminate between these different decays. And of course, I am obliged to show you that we also have some new physics for each, although, I mean, being serious, the demonstrator is mainly there for the backgrounds, but you can look at some models. Nevertheless, with 4 tracks, the particles produced in B decays and then decaying to four tracks, and have some sensitivity for that also. And then the other thing I wanted to show you is that, so we're also in parallel carrying out mechanical studies for the full detector, because this is meant to be a 10-meter cube, and really the mechanics is one of the major challenges, if not the biggest challenge. And so these are just engineering drawings to show you that there's a dedicated effort going on to figure out how we can actually fit this into the available space, and how, where to put essentially the accesses so you can go inside and do maintenance on this thing, and so on, and to what extent we can reuse some of the existing infrastructure that is in the cavern for this. Okay, so in conclusion, I hope I've shown you why we still think as the CODEXb collaboration that this is an affordable detector which certainly complements LHCb's reach for LLPs in transverse direction and that of other proposed detectors. So obviously, as everybody else, we've been affected by COVID, but I mean, the demonstrator is very much going ahead, and should well, if the situation doesn't deteriorate any further, should take data during run 3. We've also made significant progress on the mechanics since the EOI. And yeah, once we have data from demonstrator and we can finalize the detector design, hopefully, and then go ahead with scaling it up during LS3 and LS4. Okay, thank you.
Thank you very much for your talk. Any questions?
Yes, I do have a question, Vava. Ciao, Gaia speaking.
Okay.
Can you go back to the K-long background? So what is going to protect you from that? The shielding of lead shielding that you are planning to build?
Right. So exactly. So the lead shield with the active veto, and the point. I mean, the point is you can see in this table.
You have to go down by 7, 8 orders of magnitude, right?
Yeah, that's right. So you see on the left what you expect once you have a shield, and you see on the right what you expect without a shield. The whole point is to calibrate this in data so that we want to calibrate the right-hand side, because what we saw in this measurement campaign with the scintillators is really something like an order of magnitude smaller backgrounds than what we were expecting.
Yes, these are, I know, yeah.
Yeah, so this is what we want to calibrate this to really observe directly, and hopefully, so studies are ongoing, but hopefully you should be, with the multi-track decays, you should be able from the topology of the decay to even differentiate between different K-long decays to some extent. So then we can really isolate which component is which. And because of course we want to make the shield as small as possible for obvious practical reasons.
Of course. Where do these K-long come from? Do you know?
Well, there's a, I mean,
Because
some of them you have direct production, and then you have.
You don't have the veto, no? No, you don't have the shielding.
No, sorry, no, of course, no. So for the demonstrator, when you don't have the veto, this is all just produced. I mean, we simulate with a pileup of 6, which is what we expect for run 3, and this is all just produced in the.
Okay. Because I naively would have expected that the strange hadrons would have been produced forward.
No, you're absolutely right. They are, but you have CODEXb covers quite well. Even CODEXb that covers a non-zero solid angle.
Are you sure that is not a secondary production from other objects produced, not forward? I don't know.
I think I would have to go and look at the detailed numbers. I don't think most of it is secondary production. I think there. I mean, right? You remember the plots that even for beauty and charm, it's true that there's a lot of production in the forward region, but it's also true that max is that the most probable value for the production is still central, and we're sort of the eta range covered by Codex beta is sort of between central and forward. We're not at a right angle to the interaction point.
No, right, no, for sure. But still,
we're sort of
quite a sizable angle. So this is okay. In any case, this could be that you are picking up details. Yes.
Yeah, exactly. But that's the whole point, right? Is just to measure it empirically, and then we don't have to wonder about it. Indeed. Because we also want to validate with this secondaries which are not neutral but charged secondaries which are sprayed out by the magnet, and then and a lot of this is going to be soft garbage which should be actually stopped even by the concrete shielding to some extent. But again, you just want to measure, because we've seen one thing I didn't show you in detail, but you see the measurements for the scintillators were taken at multiple points in the cavern.
Yes, I know.
And you see very significant
letter of intent. I know.
Right. So you see very significant variations in the background rate depending on where you are in the cavern. And this kind of probably indicates to you not just a question from the interaction point, but some spraying from the magnet, maybe.
Yes.
To be understood.
Of course. Thank you.
No problem, guy. It's a pleasure.
Fyodor, you are muted. I don't know if you're talking.
Yes, I'm muted.
Now I hear you. Okay.
So are there any other questions? Because I'm taking the role of the chair. The chair disappeared. The first participant.
Unexpectedly.
No, he excused himself. Yes, so if there are no other questions, so we finished our session exactly on time. And so see you all in 2 hours and in the evening for discussion.
Okay.
Thank you.
Thank you.
Bye.
Bye-bye.
Thank you, everybody.
Thanks. Bye-bye.
Thank you.
Thank you.